Okay, for topic 2, we're going to look at dependent events. So remember, we're talking about probability for events involving and. So what I told you in the previous video is when we're talking about and probabilities, we don't necessarily see the word and, but we're looking for a sequence of events like this, then this, then this. So looking for wording like things in a row, okay, would be common. So let me get this. Okay, so and means a sequence of events. And in the previous video, we talked about independent events. That means the probability of the first has absolutely no bearing, no impact on the probability of the second or the third. Okay. With dependent events, the probability of the first does matter. Okay. So as our definition, let's go back to yellow. So as our definition, it says two events are dependent events if the occurrence of one of them has an effect on the probability of the other. So we do have some kind of effect. So that first probability is going to change the outcome of the second. The second is going to change the outcome of the third. The third is going to change the outcome of the fourth. Okay. So when you're dealing with the probability where you're looking at events involving and you do have dependent events, you have to be a little bit careful with how you calculate your probability. So if A and B are dependent events, then the probability of A and B is the probability of A times the probability of B, knowing that A has already happened. Okay, so it just this statement right here, it just means, hey, we're looking at the probability of B, but we know that A changed it. We know A had some kind of impact on B in some way, shape, or form. Okay. So you're still looking for a series of events. That hasn't changed. It's just now we know the probability of one impacts the other. Okay. So we can't use rolling a die here because the rolling of the die is always going to be independent, but we can use a deck of cards. Okay. Now, when we use a deck of cards in this situation, you draw a card and you keep it. You're not drawing a card, looking at it, and then putting it back in the deck and reshuffling. You draw a card, you hold on to it. So once you draw a card, there's no longer 52 cards in the deck. Now there's only 51 cards in the deck. Okay. So that's what we mean by the probability of the first. We took that card out. It's now changed the outcome or the sample space for the second. Okay. So let's look at the some examples of this. So example 2 just says find each probability. For part A, it says you are dealt two cards from a standard 52 card deck, assuming no replacement, meaning you draw a card and you hold on to it. So assuming no replacement, what is the probability of getting two kings in a row? So we want the probability of two kings in a row. Well, the probability of the first king, well, there's four kings, there's 52 cards in the deck. So the probability of the first card is going to be exactly what you'd expect, 4 out of 52. But now you've got one king that you're holding in your hand. Now there's only 51 cards in the deck, and of those 51 cards, only 3 of them are kings. So now the probability for that second king has totally changed. Now, for that second king, we can't say that there's four possibilities. There's only three possibilities to get a king, and there's no longer 52 cards. There's only 51. So now we're going to take the probability of the first, nothing weird there, 4 out of 52, but the probability of the second is 3 out of 51. So let's go to the calculator. And you can do this two ways. So when you're in the calculator, you can do parentheses 4 divided by 51. That's your first, or not divided by 51, divided by 52. That's your first probability. And then you multiply it by the second, which was 3 out of 51. Hit enter. And it's going to give you some crazy decimal. And then you go to the math button, which is directly below the two colorful buttons. So you go math, first menu, first option, and then hit enter again, and we get 1 over 221. Now, that's one way you can type this in. The other way you could type this in is you could type in the template for a fraction. So we could go alpha y equals, choose option 1. Our first probability was 4 out of 52. Hit the right arrow to leave the denominator, multiply, and then go alpha y equals again. And we get 3 over 51. The nice thing about this option here is most of the time, I don't want to say always, but most of the time you'll get something that reduces nicely. Every now and again, the calculator gets numbers that are so kind of complicated to work with, it'll just give you decimals. But generally speaking, when you do this method, it multiplies and it simplifies. all at once. Okay. Either way you slice it, we get 1 out of 100 or 1 out of 221. So the probability of two kings in a row, 1 out of 221. Okay. Looking at part B, it says you are dealt 3 cards from a 52 card deck, assuming no replacement. Again, you draw a card, you keep the card. What is the probability of getting 3 hearts in a row? Okay. So the probability of 3 hearts, well, the probability of the first heart is exactly what you would expect. How many hearts are in the deck? How many cards are in the deck? So we know we've got 52 cards in the deck to start. And of those 52 cards, 13 of them are hearts. But now you're holding a card and it happens to be a heart. So for your second draw, you've only got 51 cards. And of those 51 cards, only 12 are hearts. So now you're holding 2 cards, okay? So for your third draw, you no longer have 52 cards. You no longer have 51 cards. Now for your third draw, you have 50 cards. And of those 50 cards, 11 are going to be hearts, okay? You can do this a few ways. So I've shown you how you can type fractions in just using parentheses and division. I've shown you how you can use the template feature, but there's another way you can do this. Instead of typing in 3 separate fractions, what we can do is we can understand that when we're multiplying fractions, we're just multiplying the numerators and then we're multiplying the denominators. So we could type this in as just one fraction where we multiply all of the numerators in a single numerator. We multiply all 3 denominators in a single denominator. So let's do that. So let's go to the calculator. We'll save ourselves. I mean, this isn't going to be like some life-changing shortcut, but it'll save you a little bit of time. So we're going to go alpha y equals, and we're only going to have to do alpha y equals 1 time because now we're going to type in the product of all of the numerators. So we had 13 times 12 times 11. And then we're going to type in all of the denominators. We had 52 times 51 times 50, and we hit enter and we get 11 over 850. And remember, the cool thing about using this template feature is it automatically reduces your fraction for you. So let's go back to the worksheet and we have 11 over 850. And that's your probability. So of course, if you wanted to multiply these out individually, you could get some product for the numerator, some product for the denominator, and then you could simplify it. Or on the TI-84, it'll simplify it for you if you use that template feature. All right, let's look at another example that's kind of real world-ish. Okay. So part C, you bought a box of, let's see, you bought a box of a dozen filled donuts. They all look the same from the outside. So imagine these little round donuts with powdered sugar on top, but then they have some different kind of filling inside. Okay. 6 are chocolate filled, 2 are lemon filled, and 4 are blueberry filled. You select a donut, eat it, and then grab a second. Okay. What is the probability that both donuts will be chocolate filled? Now, hopefully this kind of brings home this idea of dependent events. Once you take a donut and eat it, the box of donuts is no longer the same. It's missing 1 donut, okay? So let's see. We want the probability of 2 chocolate filled, okay? So the first probability is just whatever you'd expect. We know we have a dozen donuts to start. Of those dozen donuts, 6 of them have chocolate filling. So we would get 6/12 for our first donut, but we have eaten that donut. We've consumed the donut. There's no bringing that donut back. There are no longer 12 donuts in the box. Now only 11 of them are in the box. And of the 11 donuts in the box, only 5 of them are chocolate filled. So we can go ahead and do our multiplication here. Remember, we have 6 times 5 over 12 times 11. You could almost do this one in your head, but let's go ahead and go to the calculator. So remember, on the calculator, we go alpha y equals, okay? Alpha y equals, we'll pull up the fraction template. And for the numerators, we had 6 times 5. For the denominators, we had 12 times 11. Hit enter, and we get 5 over 22. So 5 over 22 is the probability of getting 2 chocolate-filled donuts. Okay. Now, if you have the printed set of notes, like if you're in my face-to-face class and have the printed set of notes, there is a typo in part D. Okay. I apparently can't add. So it says you bought a box with 2 dozen chocolates. Okay. They all look the same from the outside. So imagine those like fancy, like Russell Stover chocolates, but in this case, they all look the same. Okay. Of these, 8 are caramel filled, 6 are maple filled, 6 are almond filled, and 4 are chocolate filled. So they have some kind of chocolate truffle center. Okay. That should say 4, not 2 for the chocolate filled. Okay. You select a chocolate, eat it, grab a second. Okay, let me read that again. That was terrible reading. Okay. You select a chocolate, eat it, grab a second to eat. They are both so good that you go for a third. What is the probability that you got a caramel, an almond, and a solid chocolate? Okay. So for our, and we're going to go in that order. All right. So we want the probability of a caramel, almond, and chocolate. Okay. And again, we're going to go in that specific order. All right. I don't know that it necessarily matters, but that's what we're going to do. Okay. All right. So for the first one, we're looking to get a caramel. Now we know there's 2 dozen chocolates. So 2 dozen is 24. So to start with, we have 24 chocolates. And we know that 8 of the 24 have caramel filling. So we have 8 over 24 for our first chocolate. Now remember, we ate that chocolate. There's no longer 24 chocolates in the box. There are 23. Okay. And of those 23, we're expecting an almond for the second chocolate. So how many were almond? Let's see, there were 6, and we still have 6 almond because we know the first was caramel. And then for the third, we're looking to get a chocolate. It's a solid chocolate. So let's see, that was 4, but we no longer have 23 chocolates. We only have 22. So let's see what we get. For our numerators, we had 8 times 6 times 4. For the denominators, we had 24 times 23 times 22. I'm not going to do this one. I'm not going to switch screens because I've already shown you how to use the calculator. So to save us a fraction of time, I'll use my handheld. 24 times 23 times 22, and I get 4 out of 253. So the probability of getting a caramel, an almond, and then a chocolate, a solid chocolate, would be 4 out of 253. Okay, and hopefully you get the same thing when you use your calculator. All right, 2 more examples. It says for part E, you have a bag with 12 marbles, of which 4 are blue, 5 are green, and 3 are red. You close your eyes, select a marble, keep it, okay, and then select another. What is the probability that both marbles will be red? So we want the probability of 2 reds. Okay, well, we know we have 12 marbles to start, and of those starting 12, 3 of them are red. So the probability of the first red marble is 3/12, but we grab a marble, we hold it. So we're holding a red marble in our hand. Okay, that means for our second draw, we only have 11 marbles, of which only 2 are going to be red. So the probability here would be 3 times 2 over 12 times 11. And let's see, we could probably do this one in our head. We get 6 over 12 times 11. So 6 goes into itself once, into 12 twice. So you should get 1 over 22. Okay, so just read these questions very, very carefully because in the previous video we had an example with marbles again. But in that case, you drew a marble, you looked at it, you put the marble back. So those were independent events. The probability of the first draw didn't really change the probability of the second because you replaced the marble. In this case, you hold the marble after you take it. You don't put it back in the bag. So the probability of the first does impact the probability of the second. Okay, so part F, you are at a July 4th party. There is a cooler with 36 cans of soda. 12 are Diet Coke, 8 are Dr. Pepper. Let's see, 10 are Sprite, and 6 are Orange Fanta. It is getting dark and you cannot see what you are grabbing. If you grab one soda for yourself, and I said one soda for yourself and a second for your friend, what is the probability that you will grab a Dr. Pepper and a Diet Coke? Okay, so the probability of a Diet Coke and a Dr. Pepper. Well, when you grab that Diet Coke, we know there are 12 Diet Cokes to begin with. And at that point in time, there's 36 cans of soda in the cooler. Okay. So now you've got your Diet Coke in your hand. That means there's no longer 36 cans of soda in the cooler. There's only 35. But of the 35 sodas in the cooler, 8 of them are still Dr. Peppers. Okay. So let's see, we get 12 times 8 over 36 times 35. And again, since I've already shown you how to type this into your calculator, I'm just going to cheat and use my handheld. So we go alpha y equals, for my numerators, I have 12 times 8. For my denominators, I have 36 times 35. And this reduces to 8 over 105. So the probability of getting a Diet Coke and a Dr. Pepper is 8 in 105. Okay, so that is the deal with dependent events. Just read these again. I can't say it enough. Read these questions really carefully and think them through logically. If you're grabbing cans of soda from a cooler, you grab a Dr. Pepper and you're holding it, that means that's going to slightly change the probability of getting a Diet Coke on the second draw. Same thing with donuts and chocolates. If you take a donut and eat it, that obviously is going to impact the probability of each draw after that or each selection after that because you've now changed the sample space. Okay, so again, when you're dealing with dependent events, you look for the probability of the first times the probability of the second, assuming that A, the probability of the first, changed the sample space for the second one. Okay, so that is dependent events. Okay, and I think we've got one more video. Yeah, one more video where we talk about conditional probability.